All right, we'll get started. So a couple of things before we start. Turn down that. Is that better? Better level? 1, 2, 3. Okay. Can you hear me at the back? Yep. Okay. So a couple of things before we start. First, we're still considering Piazza. I want to do one more survey. I want to see who has used or is using Connect, who has used or is using Piazza. Of course, you could be in both camps. I want to get a sense of how much you're reluctant to use Connect is because you haven't used it, and you've heard how bad it is, versus you're familiar with Piazza and you've used it. So if you could just put up your, question? Yeah.
What do you mean by using Connect? Like using it for discussion or just
Using it for any purpose. Yeah. Okay, so if you could put up your green card if you've used or are using Connect, and your red card if you are using or have used Piazza, that'll give us a sense of that. Okay, please. Okay. So some people, quite a few are just Connect.
you don't mind using both?
Quite a few are just Piazza, and even more of you are both. Okay, so it's pretty balanced. That's interesting. Okay, so we're going to check it out some more. There is a problem getting the class list in, and using two different. We've all set up for Connect, and changing this far into the course is a pain. So there's a reluctance to do that. And I was interested to see how Piazza, for commercial reasons, managed to message me with a bunch of people asking me to use Piazza for this course. It was an interesting strategy by Piazza. If we used Piazza, I wonder if Connect would do the same thing. So, okay, if you don't have your color cards, get them there. The other thing is I've heard from one of the TAs that you're having some confusion about this states versus features versus relational representations. Okay? Now, who would say has some confusion about that? Just say, put up your hand about that. Okay, quite a few. That's interesting. Okay. So I'm surprised you didn't ask me about it before. I could have gone over it some more. I will go over it some more in this lecture. The book is very explicit on it. I'm assuming you've all read the book. I could be wrong, but I really think it's worth reading the book. You've all got it. It's free. Use it. But I'm also quite happy to take questions on it at any time, now or later, but we will be doing some more examples of that in this course, in this lecture, okay? And lots more in the course, of course. Question, yeah? Okay, the hand-in box should be in ISIS level 2. It's in the X-Wing, yeah, it's X-Wing level 2, yeah. Okay, any other questions? As I say, I'm happy to take questions at any time about anything in the course, at any time. Just say, especially at the beginning of the class or at the end of the class, or in my office hour. I have an office hour after this. Yes?
Question about the states feature. I missed the answer for there was a question on the second slide of the slide.
Okay.
I missed the answer for that question, so I was hoping that we could go through that. It's about the university example.
University example? You know what? I'm going to do another example which is very similar, and if you still don't get it, we can do it after class, but it's going to be very parallel to that one. Any other questions? I mean, the university example just said, there are 2 students and 2 courses, right? That means there are, well, I won't do that one. I'll do the next one. I'll do the one we're going to do. Yeah.
For electronic copy, which folder should we put in?
For which one? For
Using the hand-in for the...
using hand-in, yeah.
What folder should we put in?
What folder? I just want one document, right? One PDF document. You should be able to just hand it in for this class. If you go to the link, there's a web interface to hand in on the course page, which should be sufficient. Has anyone else had trouble with hand-in? We should have the dates correct now. It should be working. Okay, so you can talk to a TA or me after class about that if you can't get them. Any other questions? Okay, good. So what we're going to talk about today is search. And the first thing before you do anything is say, why am I interested in this? You know, what's the point? So we'll do, again, we've already done a little bit of this in the motivation slides earlier, but we'll do a little more on search. And then we'll talk about a simple search agent with examples and a general search procedure. Okay? So we're looking at search, we're looking at deterministic worlds and agents, static worlds, so we just have to make essentially one decision. That one decision could be an entire plan because of the very limited nature of the worlds we're dealing with. They're deterministic and so on, as we'll see. Okay? And we're dealing with state-based representations. We explicitly list all the possible states of the world. There could be an infinite number of them, but we do explicitly list them or give you a way to generate all of them if it's an infinite number. Okay? So we've already mentioned checkers, unbeatable checkers program, chess used for search. But also, not just in this module, but as we go into constraint satisfaction problems in Module 2, constraint optimizations, we've talked about how critically important they are in modern industry, so-called operations research areas, when you're doing various kinds of constrained optimization problems like linear programming, mixed integer programming, and so on. The planning module will use search and various problems in game AI. And there's I mentioned this before, that if you're building an agent that is autonomous in an AI system, an AI game system, you're going to want to have something that this is Infinite Mario. So this guy has to navigate this one-dimensional world all by itself. So what you're seeing is little Mario there. These are his plans. These red lines represent the planned trajectory based on what it can see. It can only see what's on the screen. That's what its knowledge is. And you can see it's doing pretty well. So you can check that out. I put a link on the lecture slides to Mario. It was kind of cool. Maybe we should do it again because you probably didn't see it. So you can see all the possible paths it's looking at. It rules out the ones that are blocked. And as soon as a new obstacle comes into view, it may change its idea of the best route. Anyway, that's all done with A-star search, which you'll be learning here, if you don't already know. So hopefully you're now all motivated. What else do you need? Right? I'll give you some more examples of a search agent. So the basic problem in AI is that we're solving some of the hardest problems known to computer science. That's why it's the most challenging area of computer science. Because we can often recognize a solution, but we don't know how to generate one. Like we know when Mario's successfully gotten through that obstacle course, but we don't know how to find a solution, right? So the simplest minded thing you can do then, if you know how to generate solutions, just generate all possible solutions and test each one to see if it's good, or if it's a good solution or not. That's a bad algorithm because obviously it's exponential in typical cases. You know, you're generating all possible possibilities, all combinatorial possibilities, and testing each one. It's generate and test. But we can do better than that. Often you can generate partial solutions. But we do know that search is a fundamental part of almost all AI. because we're solving what are called inverse problems instead of direct problems. Like graphics is a direct problem where you've got a three-dimensional representation of an object. You want to produce a two-dimensional image or movie of that object or objects, right? The AI version of that is to do it the other way around. It's the vision problem of you've got a two-dimensional image or images, and you want to infer what's out there in the three-dimensional world. So that's what's called the inverse problem. The direct problem is the graphics problem. The inverse problem is the vision problem. And that's typical of almost all AI problems. You're solving inverse problems. So how we're going to search for a solution is enumerate a set of potential partial solutions. And we're going to check to see if they're already solutions or if they could lead to a solution. That's domain dependent how we do that. But the generic idea will be common to all search problems. And you have to be able to recognize a solution once you see one. We call them solutions or goals. Often we use the word goal here, right? So generically, this is called generate and test. But expanding it, we can say we're generating potential solutions and testing. And even better, let's generate potential partial solutions and test. And if you can generate a partial solution and test and find out it could not possibly lead to a solution, you're probably eliminating an exponential number of possible solutions. So it's a big win. And the earlier you can do that in the process, the more you cut off. And that's the kind of thing we're going to be trying to do. Rather than generating all possible solutions and just accepting the ones that are good, testing them all, because it's so expensive to do that. If we can generate small numbers of partial solutions and cut off everything as soon as we realize it couldn't be part of a total solution, you're going to be much more efficient. So that's the basic idea to keep in mind. Okay, so these are the assumptions we're making. It's a deterministic search agent. We've got a goal-driven deterministic agent with perfect knowledge of the world. It knows where it is in the world. It knows what all the possible states are in the world. It knows what it can do in the world. There's nobody else that can do anything in the world. There's no opponent. There's no chance. Okay? There's no one even cooperating with it. It's the only thing that can change this world. Okay? That's critical for all of this to go through. So it's a single agent. And the environment only changes when the agent acts, and it changes in known ways, known to the agent. Okay? Deterministic actions, so the agent perfectly knows the actions that can be applied in any given state and the state that it will end up in if you apply an action in a given state. Not all actions can be applied in all states. There may be preconditions for actions to apply in a state, but if it applies, you know what will happen next, what state you'll be in next. You don't even have to open your eyes to look and see, because guaranteed the world will change the way you think it'll change. Right? These are the simplest assumptions we can start with. The agent is in a given start state, or there may be a set of states, but usually we have a single start state. And we're given a goal, which is usually a subset of all the states. You want to be in at least one of those states. And so the solution is a sequence of actions taking the agent from the start state to a goal state. That's a solution. We also call it a plan. It's a plan in the sense of do A, do B, do C, do D, stop because you're now in a goal state. You know you're in a goal state because you've done all this reasoning in your head under all these assumptions. The world has to work out the way you thought it would, right? So I call this an omniscient fortune teller, right? Omniscient means knows all. It's just a fancy word for all-knowing. Omniscient fortune teller means fortune teller means it can perfectly predict the world. And so if those assumptions all hold, then you can use this paradigm. If they don't, you've got to modify it somehow. So let's check out your card situation. So a perfect, simple deterministic search agent has perfect knowledge of the environment, perfect knowledge of the effect that its actions have, both of the above or none of the above. So whip out a card. Let's move right on here. If you were awake for the last slide, you got this one right. Yeah, green is good. Thank you. I'm not going to pick on people to explain why you got the wrong answer. That wouldn't be fair. But if you didn't get what I got, you might go back and look at the slide more carefully, or ask me, or ask it to you. So here's the formal definition. We have a set of all possible states. So it may not be given as a list of possible states, because it might be infinite. That would be hard to do. So you might have a way of saying, here's a start state, and here's a generator function that applied to any state will give you a set of new states. We'll deal with that later. For now, let's just assume they're all given explicitly. You're given the initial state, set of actions. Often we call them operators. They're called operators because they apply to a state and they give you a new state. Just one new state, right? Because there's only one thing that can happen if you do X in state Y. You get state Z for sure. Okay, so they're operators applied for each state and each operator. If the operator is applicable, as I say, it's not always applicable. You can't always do things like, if I want to pick up a block from the table and there's no block there, I can't use the pick up block operator, right? If the operator is applicable, it defines the successor state, singular, the state the agent would end up in. The goal state is either an explicit set of states or it's a predicate on states, which says for any state it'll tell you either true or false, this is a goal state or it isn't a goal state. Again, let's assume that for now, explicit set of states. And we're going to worry later about the path cost. Some actions may be more expensive than others, and we'd like the cheapest possible solution, the cheapest plan, by summing up all the costs of all the different operators. But let's assume for now all the operators cost 1 unit, and we just want the shortest path. So we'll do 3 different domain examples. Say I'll look at states versus features versus relations in this example. So we're talking about a delivery robot, a vacuum cleaner world, and an 8 puzzle. So you've read about this in chapter 1, section 6. This guy's delivering stuff around the computer science department. It happens to be starting here, and it wants to be over there. It's got a package for the person in this room. You can only go through doors in the direction that they open. So you can only go through that door that way. You can't go through this door from here to here. You can only go from there to there. Because you can only push on the doors, right? If you push on doors swing the wrong way, it won't open. That's what it says here. So that's the problem. How do I get from there to there? And we're just going to worry about the bold locations just to simplify the space a bit. So we immediately abstract that into a graph. The search space for the delivery robot. These are all the possible places it could be. So these are the states, essentially. The state here is just the position, the XY position of the robot. It just happens to correspond to Euclidean geometry here, right, where you are in 2-dimensional space. But it could include more. It could include the orientation of the robot, whether or not it's carrying a package, etc. But for now, we just want to get it from there to there, so we just worry about the position in space. That's all we need to know about the state. And we're going to start here, and we want to get there. All right? No, there. There. R1, 2, 3. Okay? So it's clearly a graph search problem. And you could use, I don't know, the transitive closure on the arcs. So we could just use any one. I mean, how many of you know what depth first search is? Okay. Third of the class. How did the rest of you get to third year without knowing? Maybe you do know and you're lying, or you just don't want to admit it. Anyway, we're going to do depth first search. Don't panic. But those of you who've seen it will get a little bored in that section. So we could use depth first search. We could use a variety of methods, but eventually you'll see that there are roughly, you could go directly, obviously. The best thing is to go towards the goal whenever you can. So that's my direct route, but I could also start wandering off this way and do that, or go this way and do that. Probably 3 different routes that I can see there, right? The vacuum world. So this is a robot vacuum cleaner. It will start with 2 rooms. R1 and R2. Each room is either dirty or not. This is dirt. This is clean. And this vacuum cleaner can either be in one room or the other. And if it's in a room and there's dirt in the room, it can suck it up, so to speak, right? So we obviously want to be in the world where both rooms are clean. We probably don't care where the vacuum cleaner is as long as the rooms are clean, right? And we're going to start with a dirty world. So, as I say, we'll look at either state-based or feature-based representation. So this you could think of as feature-based, right? I've said room 1, dirty, not dirty. Room 2, dirty, not dirty. Those are the features possible, right? The dirtiness of each room. There's 2 different features there. They're each binary or Boolean, right? And there's another feature where the agent is, right? So how many features do we have? 3. Right? 2, 1 for each room and 1 for the agent. Right? And so if we have 3 features, and they just so happens they're both binary, the agent could be there or there, the room could be dirty or not, how many states would we have? 8, right? 2. If we only had one room being dirty or not, that would be 2 states. If we had 2 rooms that could be dirty or not, as we do, that would be 4 states. But we've also got to say where the robot is, right? That's another 2 possibilities. So 2 times 2 times 2 is 8. 2 cubed in this case, right? Is that clear? How we got from 3 features to 8 states. Okay? So there are the 8 states. I've drawn them all out, right? This is the dirty world with the robot there, dirty world with the robot over there. It's a different state. It's equally dirty, but the robot's in a different place. And these are where I want to be, right? And the operators, or the agent, can move left or right, or it can suck. And goal might be just no dirt in either room, right? So these are both good states to be in. So let's generalize this problem. It's a bit boring to have only 2 rooms. Suppose we had K rooms. Get your cards ready, get your thinking caps on. How many states do we have? There are K rooms. How many different worlds could we have? How many ways could this world exist? How many different ways could we position the dirt in both rooms and the robot in one of the rooms? So just go through it systematically. Here are K rooms, 1, 2, 3, 4, K. All right? There's 2 possibilities here for dirt, 2 for here, 2 for here, 2 for here. So just considering the dirt, which is the easy part, it's 2 times 2 times 2 times 2, K times. That's 2 to the K. All right? Now, it would be easy to make a mistake and think, well, I got 1 more for the robot. But the robot can be one of K possible rooms, right? So I take all the possibilities. I'm seeing lots of green, which is good, so you're grokking on that. I see lots of possibilities for the states. There are the state possibilities. But for every one of those, the robot could be in a different room, and there are K possible rooms. Right? It's just a simple counting argument. K times 2 to the K. Okay? If you don't get that now, we should stop. We should ask. Hopefully I've hammered it home hard enough. Okay? Yeah. Okay. So I need to know, I've just got these K rooms. I've got nothing in them for now. Let's suppose we've got the K empty rooms, right? How many ways could I end up with different worlds with those K rooms, right? I could put dirt here, or I could not put dirt here. That's 2 possible worlds. Dirt here or not dirt there. That's 4 possible worlds. Dirt here or dirt not here. Given all these other possibilities, that's 8 possible worlds now. I multiply by 2 every time I add a room, right? So that's where I get the 2 to the K from. But now, so I've got all these different configurations of rooms with dirt in them. Now I have to decide, I've only got 1 robot. That's the key. If I had K robots, they could either be in or out of the room. That would be a very different story. But I only got 1 robot to put in one of these K rooms. So for each one of those dirt configurations, I can choose a room for the robot, and that gives me a new configuration. That's why I have to multiply K by 2 to the K. Okay, has everyone got it now? Good. Okay, so let's talk about the search space. What are the possibilities, given these operators, or as I say, that's a synonym for actions. You can go left, you can go right, you can go suck as the robot. And the successor states describe the effect of each action applied to each state. So there's the initial state. And if I go left, I'll hit the wall, so nothing will happen. But I can think of, just that's an action that returns me to this current state. I didn't say it had to be a different state. It can be a no-op, right? In this case, it would be. If I go right, then I'll go into this other state. Same dirt, I haven't sucked, so the same dirt's there, but the robot's over here now. If I go right again, I'll end up back there. If I go left again, I'll end up back here. Okay? So I haven't sucked anything yet, but if I did suck, then I would remove this dirt and go to this state. All right? There's the suck action. Notice if I sucked again and I've already sucked here, nothing happens. It's a no-op. I come back to the state I'm in. You've already sucked the dirt up. If you go left, nothing happens. But if you go right, you go there. And you have to go right to suck up this dirt, and then you end up down here, and that's one of the goal states. So that would be a good solution, right? So you can see this graph has lots of cycles in it. It's got loops on the nodes. It's got cycles here. It's got all sorts of nasties. And that's often the case in the search space. Okay? You can't unsuck. So once you've sucked, you couldn't dump the dirt. Maybe you can, but this robot cannot dump the dirt back on the carpet. So you're always moving down with the suck actions. And that's kind of a monotonic process. Okay? The 8 puzzle, I think you all know what this is. You're given a slider puzzle. You've got to move these things around until you get them in 1, 2, 3, 4, 5, 6, 7, 8, some arbitrary new order. There's some you can't solve. It's an interesting proof to show that you can only solve half of these. If you randomly choose a new goal state, you can only solve half of them because there are even and odd permutations of tiles. It's an interesting side remark. You can try to prove that if you're bored with this. It's easiest to think about just moving the blank rather than moving tiles, because then we think of the blank as number 9, say. And you can always move the blank down or sideways if you can move it. It's in the middle, you can move it in any 4 directions. Right? So what describes a state? A state is just a description of where they are. So you could think of, if you call that number 9, and I could label these tiles 1, 2, 3, 4, 5, 6, 7, 8, 9, some random arbitrary ordering of the things, and I could just write down a vector of the numbers 1 to 9 in a certain order. And that would be a good state description for this problem, right? And the operators are moving the blank. And you have to describe how the operators would affect that representation. Right? So, but we won't worry about how we represent it. We'll just do it visually here. Or you could even use an array if you wanted to. Like that. And these are the moves. You could move the blank up, or you could move it left, or you could move it down, or you could move it right. You end up with new states. And so on. Notice here, there are only 2 operators. If it's there, you can only go left or right. You can't move it up. There's no point in moving it down, because then you go back to a previous state. So whenever you're thinking of generating a new state, you could say, I've already seen this state. There's not much point in going back to one you've already seen, because any solution will have to get somewhere else, right? Does that make sense? So this slide just says what we just said, I think. States, each state specifies which number blank occupies each of them. Any representation that does that, you could use a list, you could use a one-dimensional array of 9 positions, you could use a 3x3 array corresponding directly to the board. You choose. It doesn't really matter, I don't think. Well, some would be slightly easier to work with in terms of how the operator changes the representation when you do an action. So, think again. How many states are in this world? How many possible ways can we configure this tile? If we could sort of remove all the tiles from the board and then put them on one at a time, that's a way to think about how to generate the states. How many possible ways could I do this? Okay, so we got a fair inhomogeneity. We have a strong predominance of 9 factorial, which I think is the right answer. I mean, to think about it this way, if I have this blank 3 by 3 array and I've got the 9 tiles here I'm going to put in, I take tile number 1. There are 9 positions I could put it in, right? So that's 9 possible states so far, partial states. I take tile number 2. I've only got 8 positions left for it to go in, right? I could put it in any one of those 8. So that's 9 times 8 possible states, 72. Take tile number 3. I can put it in. It's only got 7 possible blank spaces left. So it's 9 times 8 times 7, right? Get it? Down to 1. When I get to the last tile, there's only 1 slot left where it has to go there. So it's 9 factorial, 9 times 8 times 7. Yeah.
So what if you put that initial tile in a different spot? Wouldn't that give you another whole set of states?
No, because I would have counted that state in my previous way of generating it. Okay? So if I think, oops. So I've got the tiles here, right? And I'm going to take each one and put it in there. So I could take this guy, I could put it in there, 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 put it in there, put it in there. Okay, so that's 9. I've now got 9 possible worlds. Okay, and then, but I've put it in all possible positions for 1. So I'm making sure I'm counting every possible state this way. Okay, and then for 2, once I've decided where 1 is, suppose it's there, then 2 could go any one of the other 8s. 8 spaces. I mean, it would be a different 8 for each different position of 1, but it's still 8 times the previous number. Okay? Does that get everyone? Okay. Okay. So everyone gets that that's 9 factorial. That's good. So, as 3 different examples, what's a generic search algorithm? Start at the start state. Evaluate which actions can lead us from the states that have been encountered in the search so far to new states, and stop when you get a goal state. That seems like a good algorithm. Except what happens if you don't encounter a goal state? It'll never stop, so we have to worry about that. But we're going to use formal definitions. We're going to use digraphs, directed graphs. And I'm assuming that all of you are familiar with directed graphs, but the notation always slightly changes. We're going to talk about nodes or vertices. So a directed graph is just 2 sets. N, a set of nodes, and A, a set of arcs. Each arc is an ordered pair of nodes. And we say that N2 is a neighbor of N1 if there's an arc from N1 to N2. That is, if N1, N2 belongs to A. So this is an ordered pair, this bracket notation. Okay, N2, N1 is different from N1, N2. There's not an unordered set. So that's why it's a directed graph. It goes from N1 to N2. Usually those are called arcs, but sometimes we loosely call them edges. Sometimes edges means arcs in both directions, but we'll only worry about directed graphs from now. And then a path is any sequence of nodes from N0 to Nk such that each adjacent pair is an arc. Right? I mean, this is fairly obvious. A cycle is a non-empty path such that the start node is the same as the end node. Okay? So, this is just doing the obvious. If I have N0 and K, then if I have N1 and 2, 3, if I have a sequence of arcs that gets me from N0 to Nk, each of these is in the set of arcs I've told you. And this is just an algebraic definition. I can also define a graph by just drawing a picture of it, obviously with the nodes and the directed edges. And we're going to talk about search graphs. Do not confuse search spaces with search graphs, okay? We talked about search spaces, which is a set of all possible states and ways you can move from one to another. we're going to essentially search that space, but we're going to use another graph, which we'll call the search graph, to represent that search, okay? So the nodes are search states. Edge correspond to actions or operator. And given a set of start nodes and a goal nodes, a solution is a path from a start node, say here, to a goal node, say there. That's a plan of actions. Okay? Just formal definitions. And then one more thing, we have to worry about the branching factor, because that'll affect the efficiency of our searches. We'll talk about the forward branching factor. That's the number of edges or arcs coming out of the node. So the forward branching factor of this node is 3. And the backward branching factor is the number of arcs going into the node. In this case, the backward branching factor of this node is also 3. And we know that if you have a tree, if I have a tree with the root here, and I have b successors at each node, where b is equal to 3 here, that's the forward branching factor, then I will get, at this level, I'll have b nodes. At the next level, for each node here, I have another b nodes here, so it's b times b squared. And so if I'm n nodes deep, if I go n levels down the tree, I'll obviously have b to the n. This is all familiar to you, I would imagine. So we get this exponential growth. Every time I go another level deeper in the tree, I get b more nodes. And we're going to worry about, say, the delivery node, sorry, the delivery robot. Here are the nodes. I've listed them out. Here are the edges. There's an edge TS male. That's that edge there. O103 TS, that's this edge here. So this and this are exactly the same graph. They're just one's represented visually, the other's represented algebraically. Given this, I can draw this. Given this, I can write that. And here's one of the solution paths. I'll represent the solution paths using this kind of arc-like notation, but just instead of just having 2 nodes, I'll have n nodes. Go from here to here to here to here to here. That's what that says. Right? That's 1 of 3, because I could also do this. I could also do this. In between, I could insert those extra little detours in there. Okay? So we're going to do graph searching. We'll have a generic graph search algorithm, and then we'll specialize it in all sorts of ways. Again, this is probably familiar to you from other courses, but we'll probably go further than you have in other courses. So given a graph, start nodes and goal nodes, incrementally explore paths from the start nodes. And the way we're going to do this is in the middle of the algorithm, I'll have a data structure called a frontier. We won't worry about how we implement that right now. It's just an abstract data type called a frontier. It's a set of paths. This is critical, not just nodes, but it's paths from the start node that have been explored. And we're going to sort of push the call a frontier because we're pushing it out into unexplored territory. Okay, you're going to start from the start, and keep pushing out the frontier in various ways. Maybe push harder here or there. It'll have different shapes, maybe, depending on the algorithm. But they'll always have this notion of a frontier. And eventually, I hope to capture a goal node. Question?
Would that depend on whether you're using them for search and for
No. They all use a frontier. They just use the frontier in different ways. Just think, we'll see that, in fact. Okay? You're talking about different search strategies, so the way in which the frontier is expanded defines the search strategy. We're going to talk about depth first, about breadth first, about uniform cost, about A star, a whole bunch of other different algorithms. So this is the generic image. We've shown the frontier as a set of nodes, but in fact, it's easier to draw it that way. It would be messy, but this node here represents this path. This happens to be a tree. There are no cycles in this graph, so whether you use the leaf nodes or the path to the leaf node from the start doesn't make any difference. But it's important to remember the frontier is this path plus this path plus this path. In other words, each of these nodes represents the path that it is the end of. So this is the ones we've all visited all together, and this is unknown territory. We don't know that they're out there. As the agent, we don't know what's out there. This is all we know about at this point. Okay? So we'll just put this into a kind of pseudocode. So the input to this code is a graph, formally defined, the way we did, a set of start nodes, and we'll be given a Boolean procedure goal, which is true if and only if n is a goal node. And that could work by looking it up in a list of possible goal nodes or some other property of the state you could use to determine if it's a goal. I don't care. You just got to give me that predicate to run this algorithm. So we'll initialize the frontier, and we'll think of it for now as a set of paths. And initially, you could just start with one start node. That's the entire set of paths we'll start with. And we'll just loop, while it's not empty, select. I'm not going to tell you yet how to select a path, but just randomly select any path from the frontier and remove it. So this is some arbitrary path from this frontier. I check the end of the path to see if it's a goal. It's critical that this test is here, not later. We'll see why. When I take the path off the frontier, I check to see if it's a goal node. Am I there yet? If so, then you return that path. And this should say output, successful path, if it terminates. Otherwise, if it's not a goal, this isn't a goal. If it is, I return it and stop. But if it isn't, for each neighbor of this is at the end of the path. It will have a set of neighbors, perhaps, maybe not. But if it does, for every neighbor of nk, add this new path, just extending the path by one node, this node, one of the neighbors, to the frontier. So I will, if nk has a branching factor of b forward, then I'll be adding b new paths to the frontier at this point. Okay? And I just continue looping. If it's not, if I haven't run out of, eventually if it's a finite space, I'll run out of paths. This will exhaust itself. It'll get starved. And it will be empty, and I'll fail. Right? If there's no goal. If there's a goal node, I'll find it before I fail here. Okay? So that's the generic. And the only thing that affects the search strategy is how do I select a path here? Which path do I choose? I could choose the longest path, the shortest path, the one I just made, the one I made a long time ago. I could add up all the costs on the path. All sorts of options here in this select, hidden here. But it's always the same algorithm. Yeah.
How is that frontier populated with paths unless you actually travel to another node?
Right here, I seed it with a start node. So
Right.
there's one path here which starts and ends at the start. Okay? In here, I select a path. Well, the only one I can select is this one here initially, right? And then I add on, if it's not a goal node, I add on all its neighbors. It'll be S, and each one of its neighbors there will be B new paths, okay? And then I just keep going. Okay, any other questions? Yeah.
What if you reach a dead end? Let's say there's 9 possible paths, but then you reach a dead end that the tree, the graph, or whatever, it stops.
Yeah, if you reach a dead end and you haven't found a goal, let's say you will fail out the bottom here. We probably should have added a test here. If frontier empty, when you come out of this loop. Here we're going to jump back and return out of here. But if you get to here, you've essentially exhausted. Frontier is now empty, so that's what you mean by dead end. There's no possible way to go forward. Then you failed. So this is really a fail. But the only way this can return a goal node is from right here. That's success. Everything else is failure. Okay? Yeah.
With cycles in your graph,
Yeah, there might be a problem, and we're going to look at cycles later. For now, let's assume that we've got trees as our search space. Any other questions? Okay, so I'm going to do one more, I'm going to do a little survey here. I just want each one of you to take one card. I'm going to ask you how we're doing in the course so far, just in terms of pass these up here. So maybe you could just sort of pass them halfway along and then pass them back I just want to get a little quick survey of what you think we could be doing better or what we're doing right in the class. So before you do that, wait till everyone's got a card. So we'll finish this lecture for now. This is the summary. Search is key to many AI agents, and we're studying the simplest possible case of search, of single agent, deterministic actions, goal-driven search in state-based world representations. Here's this generic search approach. Define a search space graph, initialize the frontier, incrementally expand the frontier until the goal state is reached. And the way in which the frontier is expanded defines the search strategy. So the next time we're going to talk about the ones you already know about, I hope, depth-first search, breadth-first search, and so on. We call those uninformed search strategies because they have no knowledge of the problem that you're solving. Okay? We've identified, these are the learning goals, which we talk about in Connect. We put these in there. This is what you should know. This allows you to test yourself. Do I know how to identify real-world examples, assess the size of the search space, implement the generic solution to the search problem? You should be able to do all those things. And this is what we're going to do next. So I'm just looking for, just point form. You don't have to write essays on these cards. There's no room for that. But just quickly tell us, what do you like about what we're doing so far? What do you want me to keep doing or do more of? You could write pro on one side. On the other side, you could write con. What do you not like? Is there anything you'd like me to stop doing, start doing instead? Anything from lecture mechanics to the way I'm presenting the lectures, or anything about the TAs, or the room, or the slides, or the fact that I don't put PowerPoint slides up, I only put PDF, etc., etc. Just anything that occurs to you. I'd appreciate getting that. So it's just a quick, early set of feedback. And just when you're finished, they are anonymous, so just drop them on the table there on the way out.